Schrodinger equation is simply a second order partial differential equation. So why is it second order? Because this is the equation shown here. So what it has is a second derivative, second order derivative. So second derivative, second order, and then there is it's partial derivative, partial differential equation, because we are only showing right now in terms of x. You could also have dependence on y and z, but right now we are just showing the partial derivative with respect to x. So second order partial differential equation. Okay, what is it telling us? Basically, it has some derivatives, and this, you might have recognized this quantity psi, which is what we call as wave function. So this essentially tells you how the particle moves, right? We said Schrodinger equation is essentially the analog of Newton's second law. So wherein the psi of x describes a particle, it's a wave function of a particle, and v of x is basically the potential energy of the system. So basically, it is how the potential is changing in a system, right? So that is v of x. I shouldn't call it potential energy, it's simply the potential of the system. And then when I know the wave function, I can actually find out what is the probability of finding an electron by calculating what is psi. If you have psi, you take the modulus of it and square it. That is the probability of finding a particle at a position x. This is finally what is physically observable. Physically, we cannot find wave function. We will only find the probability of finding an electron or a proton or whatever. All right, and E is the various allowed energy levels in the system. So with these parameters, you could write an equation of this form, and this essentially is what is called as eigenvalue problem. Okay, so you will study it if you have already not studied it, but for now you just accept this. This is a very important class of problems which are called as eigenvalue problems. Okay, where whenever you study matrix theory, you will study this. So what's happening here is you have certain differential terms, and you apply that on the wave function psi, and when you do that, what you get is the wave function again. You get back the wave function, and then the coefficient is basically what is called as energy, eigenvalue. So it's the energy of the system. Okay? So this form of Schrodinger equation is called as time independent Schrodinger equation. There is another form which is called as time dependent Schrodinger equation, but that is not really necessary for us, so I did not even mention it. Okay, we will not worry about that in this course. So this is the time independent Schrodinger equation, and we would like to solve this to understand how different material properties change. And in today's lecture, we will try to solve this in two cases. The first case is what is called as the free electron problem. Okay. So let's assume that you have a free electron, by which we mean that there is no potential applied anywhere. So V of x is taken to be 0 now. If you take V of x as 0, you can solve this and find out what is psi. That is essentially what is called as solving the Schrodinger equation. So how will we do that? So once V of x goes to 0, we can rewrite this. It will turn out to be minus h cross square by 2m dou square psi by dou x square equal to E psi of x. Right? This is the equation. We can rearrange it a little bit, and this can be written as, I'll just take the 2m by h cross the other side. So basically, dou square psi by dou x square plus 2me by h bar square psi equal to 0. So this is the equation that we need to solve. Right? Before we solve that, we will introduce a constant. Let's say we'll call it k. K is basically 2me by h bar square. Okay, sorry, k square. Let's call this as k square. K will be root of it. Okay. We will come to why this is like this. Okay. So now, if I do this, so basically my Schrodinger equation becomes dou square psi by dou x square plus k square psi of x equal to 0. So what is the solution for this? What is psi? K is a constant. So what is psi? To find out what is psi, we have to make some, guess. Let's assume that, psi of x is equal to exponential I k x. Okay, let's try to substitute and see what happens. Does this psi satisfy the Schrodinger equation? How do we do that? So you take the second derivative, essentially you get I k whole square psi, right, plus k square psi of x. This is the left hand side, right? LHS is this, and that is equal to 0. So basically, this particular solution is satisfying the Schrodinger equation. Similarly, you could also check, that exponential minus ikx will also be a solution to the Schrodinger equation. All right. So both these are solutions to the Schrodinger equation. But what is exponential ikx or exponential minus ikx? So these are what we call as plane waves. Exponential ikx essentially tells you a plane wave which is propagating in the positive x direction. Whenever there's a wave propagation, it's exponential ikx in this case. Okay. So basically, the general solution would be psi of x, because we have two solutions which are acceptable. So we can write a general solution by taking the linear combination of these solutions. So we can write psi of x equal to a exponential ikx plus b exponential minus ikx. So this is the general solution of Schrodinger equation. All right. So, I mean, we could also try to write it in a slightly different form, because we know from trigonometry that exponential ikx is simply cos kx plus I sine kx. And similarly, exponential minus ikx also we know what it is. So you could write it in another form. I'll try to change the coefficients. I'll redefine the coefficients. I'll say c sine x sine kx plus d cos kx. So this is also a solution. I mean, basically these are again some coefficients, okay, some constants. I can define them, in terms of a and b and all that. We can just compute that. All right. So basically, these are two forms of solutions which are, satisfying the Schrodinger equation for a free electron. So it turns out that the second form is actually much more very suitable for us. Okay. So we will just like you to note this equation now. All right. So this is the first problem for Schrodinger equation. It's not that complicated. I mean, it sounds heavy, but it's not that complicated, right? So now what we'll do is we will try to understand what it means, right? So we redefined, we defined k as basically k square has to me by h bar square. Okay. So the reason we did that was, if you rearrange it, you could also write energy as h bar square k square by 2m. Okay. So what it means is, we know classically, in the classical mechanics, we know that kinetic energy is basically half mv square. That you could also write it as momentum square divided by 2m. We studied this in classical mechanics. So essentially, energy in quantum mechanics can be written as E equal to h cross square k square by 2m. So this is known as the dispersion relation for a free electron. Okay. Dispersion relation for a free electron. Free electron. All right. This is important. Now, what is this telling us? Essentially, you could study this by plotting E versus K, where I'll say E is basically energy versus K. K basically captures how the momentum is changing. So this is essentially momentum, which is h bar k, right? So how is energy changing with momentum? That is captured by this EK relation or energy momentum relation. And it turns out to be a parabola. So what this is telling you is that if you have a positive k, it's essentially capturing how the energy is changing for a wave which is propagating in the plus x direction, okay, exponential ikx. So what this is telling you is that as you change K, the energy is continuously changing. Okay? So for every small change, there will be a continuous change in energy. This is an important characteristic. Similarly, for the negative K, we are essentially talking about a wave which is propagating in the negative X direction, and it also has energy which is changing continuously. And since K square is there, it's basically a mirror image. Right? So this is the dispersion relation for a free electron. It turns out that if you confine this electron, instead of making it free, if you confine it, it has some very interesting effects. Okay? That is what we would like to do now. So now we would like to solve what is called as particle in an infinite 1D potential well. Okay? 1D because we are only talking about X direction. So what we are trying to solve is, we are saying that an electron is confined to a region of space. In the X direction, let's say, it is confined to a length L. Okay, so this is the length L, right? This is the distance L. So I'll say that electron has to be confined to this region. We're calling it region 2 here. Okay, it has to be confined. It cannot go into either region 1 or region 3, which are essentially potential barrier. Okay, so these are because this is a barrier, and this is also a barrier region. That means electron cannot go there. You can think of it like, there's a potential, which is basically repelling the electron to stay in the well region. Okay, and this potential is assumed to be infinity in the region 1 and 3. That's why we are showing that it is a infinite potential. And then in between that, there is a small well which is of the length L. Okay, so now we would like to solve this. Okay, this is equivalent to telling that, let's say, if I have to give a physical example, let's say I have this, pen. I would like to solve how the electron, if an electron is confined to this pen itself, it cannot go anywhere else. So essentially, I'm talking about barriers which are surrounding the pen, and then electron is only confined to the central region, right? It's a similar problem here. So now, before we solve this, let us try to ask a simple question, which is, what is the wave function in the regions 1 and 3? Okay. So psi of x, we said that basically wave function is essentially a function that tells you that, it can be a sine x, right? Essentially, it's a function of x, right? So what is it in the regions x less than 0? Okay. Region 1 means x less than 0, and region 3 means x greater than L. Okay. What is a wave function? We are clearly telling you that the wave function, the electron cannot exist in those regions. Okay? So that means there is no probability of finding an electron in that region. So wave function has to be 0 in those regions, in 1 and 3. Why? Because if wave function is non-zero, then the probability which is given by psi square, mod psi square, that is also non-zero. That means electron can exist in that region, which is not allowed by the definition of the problem, right? We have taken infinite potential barrier, so it cannot exist. So that's why this wave function turns out to be 0 in these regions, right? Region 1 and region 3. All right. So part of the problem is solved. Now, if you find out what is the wave function in region 2, the problem is fully solved, right? So what is the wave function in the region 2? How do we solve that? Well, in region 2, the potential V of x is 0 here, right? So the way it is given, this is basically potential is 0 here and infinity on the other side. So basically V of x is 0 in region 2. So only in region 2, you could say that this is V of x is 0. So we know what the solution is. When V of x is 0, we have already done this for a free electron. So we know that psi of x is equal to c sine kx plus d cos kx. All right. So now, what are the coefficients c and d? If we know those coefficients, we are done. Okay. The problem is fully solved. So to understand that, we need to apply what are called as boundary conditions. So we need to apply boundary conditions by which we mean that we know that at x equal to or let me write it this way, psi of x equal to 0 is how much? So well, we said that psi x less than 0 is 0, and the wave function has to be continuous. That's one of the properties, requirements of wave function. So it has to be continuous. So at x equal to 0, it has to be 0. Similarly, psi x equal to L also has to be 0, because again the wave function psi is a continuous function. We cannot have sudden changes in psi. That is not allowed by the equation. So basically, since psi has to be continuous, these two boundaries at this 0, x equal to 0 and x equal to L, wave function has to be 0. So will that help us solve the problem? Well, it does, because if you have cos dependence in the wave function, then at x equal to 0, it cannot go to 0 at all, right? If there is a cos, because cos 0 is 1, so it always will be non-zero at x equal to 0. So if your wave function, the equation 1, because of this, sorry, not boundary condition 1, because of this, implies d equal to 0. Because if d is not 0, psi will basically be non-zero. Okay, that's why d equal to 0. So now the wave function simplifies to psi of x equal to c sine kx, right? Now we have the second condition, which is at x equal to L. So basically psi x equal to L, which is simply c sine kl equal to 0. This has to hold for any k. So what kind of relation should it be? So basically this implies that k times L should be n times pi. Only when your the variable in the sine function is equal to n times pi, we can be assured that the sine function goes to 0 at any k. So this implies that k basically is n pi by L. This is an important relation. Okay. So what we are seeing is k, in the free electron case, k was continuous function. You could take any value of k and then there will be corresponding energy. But the moment you confine an electron to a small potential, in a potential well like this, k cannot be a continuous function. Okay, k has to be discrete because L is fixed, right? L is fixed, and this is a constant. N is an integer, right? So it can only take discrete values. So we write it as Kn is equal to n pi by L. Just to make sure, just to denote, it's the same K, but when we write Kn, we are trying to say that n, there is a discrete n equal to 1, 2, and 3, and so on. Okay, so this is the discreteness that has come about in K. Okay, this is an important consequence of the confinement of an electron. Okay, so if you confine, so what does it mean? I have simply dropped C, okay, because C is basically what is called as normalization constant. We can actually find out what exactly it is. It turns out to be root 2 by pi in this case. But right for now, let's not worry about that constant. Okay, let's assume that this is not truly correct, but the functional form of psi of x is basically sine kx, right? So k was n pi by L. So I can write my wave function as this for n equal to 1, 2, 3, and so on. So what does it mean? We can try to substitute it. We can plot it in Python or MATLAB. Just try to do that. You'll see that the behavior of wave function psi is basically like this. You have at the n equal to 1, you have this half wavelength. At n equal to 2, you have full wave. And as n keeps increasing, you have more and more oscillations in your wave function. And we said energy E is basically h cross square k square by 2m. Now k is n pi by L, so energy becomes h cross square by 2m. I'll keep it. So n square pi square by L square. Okay, this is an important consequence. Basically now what we are saying is the energy is again discrete now. it's not continuous value. Okay, that is what is shown here. So I've tried to combine the dispersion of a confined electron and a free electron. So please don't get confused. So this part is basically the negative axis. I'm just showing the free electron. Okay, and on the positive axis, I'm showing the confined electron, just to make the difference apparent. Okay, so in the case of a free electron, you have continuous variation. The dispersion is continuous, right? This was basically E equal to h cross square k square by 2m. Whereas if you confine an electron in a potential well of length L, okay, then the energies are no longer continuous. Just the red curve is only for your reference. But it turns out that energies are basically discrete, and the discrete energy levels are given by n square pi square by L square into h cross square by 2m. So at a discrete case which are allowed, you have discrete amount of energy. Okay. So this essentially is why you could say that you call it quantum mechanics. So essentially energy was continuous in the first case, and then it became quantized. There are discrete energies which are allowed. That's why you have we call it quantum mechanics. And I would like you to study what happens when you change L. Okay, when you do this calculation, we'll just do it in a moment. But if L is large, for example, L is 1 centimeter or 1 millimeter, the energies are very, very close to each other. It doesn't really matter. When you go to macroscopic scale, for example, let's say I want to calculate the current which is flowing through my strand of human hair, right? I want to somehow, assuming that it conducts, I want to calculate that. Then the size is 1 micron. It is reasonably large, large compared to de Broglie wavelength. If L is much greater than lambda b, let's say de Broglie wavelength. If you're trying to talk of current conduction, you have to talk of electron de Broglie wavelength you have to take. So L is greater than lambda b, then no need of quantum description. Quantum description. If L is of the order of lambda b, then quantum description essential. Okay, QM essential. Okay, quantum mechanics is essential. So how does L impact? Well, if you confine the electron into a smaller and smaller dimension, then energy goes higher and higher, right? The discretization becomes stronger and stronger. You could try to put in some numbers and check this for yourself. So L is in the denominator, L square, right? So as L goes smaller and smaller, E becomes larger for the same N, of course, right? So this could also be understood by the uncertainty principle. We know from Heisenberg's uncertainty principle that delta X into delta P is basically greater than h cross by 2, right? So if you try to confine an electron in a very, very small dimension, its momentum becomes very large, right? Once its momentum becomes large, the energy also increases, right? That's uncertainty. If your X is large, for example, X is 1 kilometer, then the uncertainty in momentum is nothing. So energy is very accurately known, okay? This delta P basically tells you what is the uncertainty in the momentum in P, right? So if your uncertainty in X is very small, that means I know accurately electron is confined to 1 nanometer space, right? If I know that, then uncertainty momentum is large. If I don't know, X is very large, uncertainty in X is large, for example, 1 centimeter, then delta P is very, very small. That's it, okay? It's nothing very complicated. I'm just repeating it because I want to drive this point home. Okay, this is all there is to quantum mechanics. If you understand this, you understand quite a bit of quantum mechanics, and honestly, you could do a lot of things. So let's try to compute this. What is this? What are the energy levels which are there? So this is just a homework problem. You could try to do it. So you're asked to calculate the first 3 energy levels of an electron which is confined to an infinite potential well of width L equal to 1 nanometer. So the formula is known to you. It's just plug and chug. So you know that energy is basically, just remember, you don't have to remember these formulas. P is equal to h cross square k square. So P square will be this h cross square k square divided by 2m. and K is basically n pi by L. So h cross square by 2m, K is n square pi square divided by L square. Substitute. If you do that, you will get something like, some n square into something in the order of 10 power minus 19 joules. Okay, this is what you get. Energy in terms of joules, you'll get it like this. So this is not a very convenient thing. So what we do is we try to do, compute energy we try to give energy in electron volts, units of electron volts. So basically the way we define that is 1 electron volt, which is again another unit of energy. 1 electron volt equal to 1.602 into 10 power minus 19 joules. Okay, we use this. So please, make note of this. So sometimes, we refer to energies because EV is a very convenient unit for electron bands and all that. So 1 electron volt is basically 1 point, charge times charge joules, Q joules you can say. Okay. So if you do this calculation, you'll get this. Please try to do it yourself. E1 equal to how much? E2 equal to how much? E3 equal to how much? Okay. So, I think this would turn out to be something in the range of, I'm not very sure, but it should be something like 0.3 to, I think 3.5 or something. In that range, you will get some numbers. Okay. So please try it out and verify that you're getting the correct orders of magnitude. These are typical numbers. Okay. If you reduce L equal to 0.5, the number energies will increase. You can do all this. Okay. All right. So this is basically about how electron behaves if it's confined to a potential well. But in real life, you will almost never have an infinite potential well, right? Always the potentials are going to be finite. Okay. So we can also talk of a finite potential well, which is very, very close to an infinite potential well. In the infinite potential well, in the earlier case, in this picture, I've shown you the wave functions, okay, which are simply going which is sine of n pi x by L. You could also calculate the probability of finding an electron by calculating basically the square of modular square of your wave function. And if you do that, basically what the difference for each n, basically n equal to 1, 2, 3, 4, and 5, we are showing the wave functions here. So what this is telling you is that if you confine an electron to a region 0 to L, if the probability of finding an electron is highest at the center of the, it shows this dependence. The probability shows a half sign dependence like this. It is said to be in the first state, energy level 1. If the probability is distributed, for example, you have highest probability at 2 locations. This is basically at L by 4 and 3L by 4. Sorry, 3L by 4. So at 2 locations, you have the maximum probability of finding an electron. It's said to be in the second state. And if it's at 3 locations, L by 3, 2L by 3, and 3L by, well, it should not be that, there's slight displacement, okay? It's not L, right? L is basically slightly offset. Yeah, but the point is that if you have 3 peaks, it should be third state, and 4 peaks, fourth state, and so on. So this is the probability, okay, of finding an electron. It cannot take any other state except this. Okay. So the beauty of it is the electron, we say that the wave functions form a complete set, by which we mean that it has to take any of these states or a linear combination of these states, but it cannot take any arbitrary function in between. Okay. Anyway, we'll have to talk about it later. Now let's see what happens when the potential becomes finite. It turns out that the problem is very, very similar, but to solve this, we have to do a lot more numerical stuff, numerical, and we can actually do it analytically, but it becomes tedious. So we have used a software. We'll try to post it on a tutorial. Okay. We'll try to demonstrate this using, one of the tutorials, but essentially this is computed using numerical approach in Python. So what this is telling you is that the wave function of a finite potential well also kind of is similar to the infinite case, but the only difference is that you see that in the barrier regions, this is again, barrier, right? This is a barrier, and this also is a barrier, right? You have barrier regions. In the barrier regions also, there is a non-zero probability of finding an electron. Okay. So basically, if you look at this, the wave function psi has a tail in, so not TL, tail in barrier. There's a small probability of finding it. Okay. And if you go to, this probability, of finding, is called as tunneling, basically. What we see, actually electron is tunneling into the barrier regions. That's why there's a non-zero probability of finding an electron there. If you go to the lowest energy states, you see that the probability of finding an electron outside in the barrier is not very significant. But as the energy increases for the wave function, sorry, if the electron increases, you see that there is increasingly higher probability. If you compare the area under the curve here, this is for the fourth wave function, right? Fourth state. With the area under the curve with the fifth state, you'll see that in the fifth, this is fifth and this is sixth. This is E5, right? So this is fifth state. If you compute the area under the curve here, this location, and compare with this, you'll see that there is a higher, increasing tunneling, basically, or increasing probability of finding an electron outside. Okay. So we will use this to explain, because I could actually take, I could say that, okay, in semiconductor there are valence bands and conduction bands, and I can go on from there. But it is not very intuitively satisfying. So I'm trying to build up how energy bands come about in semiconductors. We will do that in the next lectures, next couple of lectures. But for now, I would like to stop here today. So what we did today was, we started out with defining what semiconductors are, what are the basic properties. And we said that to understand how this conductivity happens in semiconductors, it is essential to understand a little bit of quantum mechanics. Okay. So we have done a very, very quick review. We said that quantum mechanics, you have this probability of finding an electron at some point. You can calculate that, and that is given with a wave function. And to find out the wave function, you have to solve Schrodinger equation. And we took two cases. We took the Schrodinger equation when free electron, that is potential is 0, and when you have a potential well, we solved that. So in these two cases, we have seen how the wave functions behave and how the energies are changing. So we said that this idea of quantization, or discreteness of energies, is a very, very important concept. It is central to quantum mechanics. It cannot occur classically. But in a way, it is similar to what you would see. There are some analogs in the classical world also. For example, when you have a guitar, let's say, when you strum a guitar, right, you have a specific note which is produced. Why does a specific note get produced? Because you have a string of certain length, and then your tight string, and then you're plucking it. So when you pluck it, it can oscillate only at a certain mode, right? Depending on the length of the string and the tightness of the string, you could control the note that is you can play on a guitar, right? So essentially, you're quantizing the sound waves in that case. Of course, we don't need quantum mechanics to explain that. We can also, because it's large scale, we can explain using classical laws. But essentially, this idea of discrete energies or discrete waves which are allowed is there. Okay, and quantum mechanics also is sort of in a similar direction. So with that, I would like to stop here. In the next lecture, we will try to see how energy bands form, and we'll go a little bit more into depth of all these things. So I hope you understood what we're talking about. If not, please take time to review the lecture one more time, and we'll meet you in the next lecture. Thank you very much. Have a good day.